Hello, today's topic of discussion is differential equations. In this chapter, which consists of a single module, we give an overview of the differential equation. What is a differential equation? Why you are studying it? What are the solutions of the differential equations? If the solution exists, where it is a single solution or no solution or infinite solutions. These are the questions which we will be answering in this module. And we will also look why there is a need for theory of this solving the differential equations. Differential equations are used to express many general laws of nature and have many applications in physical, biological, social, economical and other dynamical systems. In particular, the origin of differential equations may be considered as the efforts of Newton to illustrate the motions of particles. These equations may provide many useful information about the system if the equation were formed incorporating the various important factors of the system. Let y equal to f t be a given function of independent variable t, then the change in y with respect to t can be represented as the derivative dy dt. In many real world process, the variable representing the important factors of the process and their rate of change are related to each other in terms of the basic scientific principles of the process. The representation of the relation in terms of mathematical forms often turns out to be a differential equation, and this may explain the vital utility of differential equation in most of the dynamical systems of modern science and technology. Let us consider an example of a simple pendulum. A weight of mass m is attached to a very light and rigid rod of length L to make a simple pendulum mounted on a pivot, so that the simple pendulum can swing in a vertical plane. The weight is displaced initially to an angle y0 from the vertical and released from rest. Now, we want to describe the motion of the simple pendulum in mathematical terms. Since the pendulum can move only in a vertical plane, the position of the pendulum can be described completely by the knowledge of angle made by the rod from the vertical position. Let yt denote the angle made by the rod from the vertical position at a given time t. To find the mathematical model, we need to use an appropriate physical rules governing the motion and simplifying approximations. In order to determine the motion, we need to impose some additional physical conditions on the system. Here we assume the following assumptions. The rod is rigid of constant length L and have no mass. The weight is assumed to be a particle of mass m. There is no other resistance to the motion of the pendulum, and the only external force present is the gravitational force acting on a point mass. Since we are assuming that the pendulum was initially displaced to an angle y0 and released from the rest, we also have y0 is equal to y0 and y dash 0 is equal to 0. At any time t, the gravitational force denoted by F is equal to mg is acting on the mass m in the downward direction. There is also a force of tension in the rod of magnitude t directed along the rod towards the pivot, and hence the governing equation of motion can be written as minus L dy dt whole square equal to mg cos y minus t and ml d2y dt square is equal to minus mg sin y, both given by equation 1 and 2 respectively. Since the motion of the pendulum is completely determined by the knowledge of the function yt, so the second equation only gives the required equation of motion, that is d2y dt square plus g by L sin y equal to 0. Thus, a differential equation is a relation between independent variables, dependent variables and its first or higher order derivatives. In ordinary differential equation, there is only one independent variable. Consider the following list of differential equations given by 1, 2 and 3. The order of a differential equation is the order of the highest order derivative present in the equation, and hence equation 1 is a differential equation of first order, equation 2 is a differential equation of second order because it got a second derivative here. Similarly, equation 3 is a differential equation of second order. Equation 1 represents a basic population model where a population is growing at a rate alpha. Equation 2 represents an equation of a particle of mass m falling freely under gravity, while equation 3 represents the same model, but now with presence of air which exerts an opposite force proportional to the velocity of the particle. In partial differential equation, there is more than one independent variable, and so the derivative of the dependent variable with respect to these independent variable are partial derivatives rather than the ordinary derivatives. And this is the basic difference between an ordinary differential equation and a partial differential equation. Let u t x y be a function of time t and the two rectangular coordinates of a point in space x and y. We consider the following partial differential equations: del 2u del x square plus del 2u del y square equal to 0, k times del 2u del x square plus del 2u del y square equal to del u del t, k times del 2u del x square plus del 2u del y square is equal to del 2u del t square. The above three equations are classical problems in partial differential equation and are widely used in application. Equation 1 and 3 are classical in nature and widely used in problems of fluid dynamics, theoretical physics and many other related fields, and are known as Laplace equation, two-dimensional heat equation and two-dimensional wave equation respectively. However, we will restrict our discussion to ordinary differential equation only. An ordinary differential equation of nth order is defined as f of t x x squared dot 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 x to the power n equal to 0, given by equation number 4. Here x to the power I equal to 1 to n is the ith derivative of the unknown function x, and f defined in some subset of r to the power n plus 2 denoted a relation between n plus 2 variables t x to the power 0, x to the power 1 dot dot x to the power n. Because of its implicit nature, f of t x dot dot x to the power n equal to 0, equation 4 may represent a collection of differential equations rather than a single differential equation. We consider the following example where dx dt cube minus t square dx dt whole square plus 3x dx dt equal to 0, which is given in the form 4. We simplify it and we get the form x dash, which is dx dt multiplied by x dash square minus 3t square x dash plus 3x equal to 0. And if we solve that, we will getting x dash equal to 0 or x dash equal to 3t square plus minus square root of 9t to the power 4 minus 12x divided by 2. So, in order to avoid the ambiguity, we assume that given ordinary differential equation is solvable in terms of the highest order derivative and written as in the following form, known as the normal form or the canonical form, given by equation 5, which is x to the power n is equal to g of t x dot dot x to the power n minus 1. A function phi t is called a solution of 5 on t which belongs to I, the interval a b, if it satisfies the following conditions. Number 1, phi t is defined and n times differentiable on I, and phi t satisfies the equation 5 for each t belongs to I. The aim of the study of ordinary differential equation is to find the unknown function represented in an explicit form, preferably in terms of elementary function. In the absence of an explicit form, one need to study the behavior of solutions by available analytical methods. Before looking for a solution or any qualitative properties, we would like to identify the class in which the equation belongs to. There are various ways available to classify the given ordinary differential equation. Some of the commonly used classification are listed as follows. It can be a linear or a nonlinear differential equation. It can be an initial value problem or a boundary value problem. Let us see the definition of linear and nonlinear differential equation. We consider the differential equation dx dt, the nth derivative, is equal to a function g. If the relation g is linear in its arguments x, x squared dot dot x to the power n minus 1, then the differential equation is called a linear ordinary differential equation. Otherwise, it will be called a nonlinear differential equation. The example x dash plus k x equal to 0, where k is a constant, is a linear differential equation, whereas dx dt is equal to sin x is a nonlinear one, because you can expand sin x as x minus x cube by 3 factorial plus x to the power 5 by 5 factorial, and hence it is a nonlinear differential equation. Let us consider the following differential equation of order 2 written in operator form Lx, which is equivalent to x double dash plus pt x dash plus qt x is equal to RT. Here the notation Lx suggests that the operator L operates on a function x to give x double dash plus px dash plus qx as its value. An operator L from Vk to Vk is said to be a linear operator on a vector space V defined on a scalar field k if it satisfies the following equality, that is L of alpha x plus beta y is equal to alpha times Lx plus beta times Ly for all x y belongs to V and for all alpha beta belongs to k. Consider the following differential equations. To check whether the equation x dash plus kx equal to 0 is linear or not, we define Lx equal to x dash plus kx, which is defined on the set of all continuously differential functions over the field of real numbers. Then we easily check that the operator L satisfies the condition of linearity given in equation number 6, and hence the differential equation x dash plus kx equal to 0 is a linear ordinary differential equation. Similarly, we can see that equations 2 are linear differential equation, while equations 3 and 4 are nonlinear differential equations. The reason behind this classification is that finding the explicit solution of nonlinear differential equations are usually very difficult, if not impossible. There are several methods that are available for solving linear differential equations, but no such general method are available for solving nonlinear differential equations. Therefore, in the case of nonlinear differential equations, the method which provide the approximate solution or qualitative properties are very useful. Consider the well known differential equation x dash plus alpha x is equal to 0, where t belongs to the set of real numbers, given by equation number 7. This equation represents the population growth model in a single species. We can easily check that the solution of this differential equation is x equal to c e to the power minus alpha t, where c is an arbitrary constant. Here we get a one parameter family of solution which consists of infinitely many solutions, and we are interested only to find those solutions of 7 which also satisfy certain other conditions, and such conditions may be represented in several forms, and two of the forms are initial conditions and boundary conditions. Say we want to find out the population of the species at any given time t, provided the population at time t0 was given as x0. So, if we have x t0 equal to x0, this will calculate the integrating constant c equal to 0, and the population x t will remain 0 for the future time. But if we put x0 equal to 1, then we can calculate c equal to e to the power alpha t0, and the population will be x t equal to e to the power minus alpha t minus t0. However, if we put x0 equal to small x0, which will imply the integrating constant is equal to x0, and hence the population will be x t equal to x0 e to the power minus alpha t. Therefore, you note that if we change the initial conditions, you are going to get different solution for the same differential equation. We now look into an example which will differentiate between an initial value problem and a boundary value problem. Given a differential equation, how will you say that this is an initial value problem and this is a boundary value problem? This example is going to teach you that. We now look into an example which will classify between an initial value problem and a boundary value problem. We consider a second order differential equation x double dash plus p plus q into x dash plus p q x equal to 0. If you solve this differential equation, you will get the solution as x t is equal to alpha e to the power minus p t plus beta e to the power minus q t. If the initial conditions are x 0 equal to 0 and x dash 0 equal to q minus p, and if we use these initial conditions in the solution of the differential equation, we will get alpha equal to 1 and beta equal to minus 1. Therefore, the particular solution satisfying the given initial conditions is given by x t is equal to e to the power minus p t minus e to the power minus q t. Let us take another second order differential equation which represents the motion of a simple pendulum, x double dash plus x equal to 0. The solution of this simple differential equation is x t is equal to alpha sin t plus beta cos t, where t belongs to R and alpha beta are arbitrary constants. Now, if you take the conditions to be x 0 is equal to 0 and x pi by 2 equal to 0, then we can easily solve the differential equation and the solution will be x t equal to 0. If we now change the conditions to be x 0 equal to 0 and x pi by 2 equal to 1, then we will get the solution to be x t equal to sin t. Please note, in the previous differential equation, we have the conditions at the point t equal to 0, and in both the cases where x 0 is equal to 0 and x dash 0 equal to q minus p, whereas in the second equation we have the solution at two different points, that is at t equal to 0 and t equal to pi by 2. Therefore, the conditions that are given at one point are known as initial conditions, whereas in example 2 the conditions are given at two different points. Hence, we conclude that the condition given at the same value of t are known as initial conditions, while the conditions defined at two or more different points are called boundary conditions. Therefore, we classify a differential equation to be an initial value problem or a boundary value problem according as the conditions are initial conditions or the boundary conditions. Next, we consider the following differential equations. The first one is 2 times dx dt whole square plus t square equal to 0. if we try to solve this differential equation, we will get dx dt is equal to minus t square by 2 square root of that, and the value is an imaginary value. Hence, we conclude that this particular differential equation does not have a real valued solution. Our second example, x double dash plus mod x equal to 0, where t lies between 0 and pi and x 0 equal to 0 and x 0 equal to a. If we are asked to find condition on A such that this boundary value problem has no solution or a unique solution or an infinite many solution, the conclusion is that a boundary value problem may have a unique solution, may have no solutions, or may have more than one solution under different conditions. The same thing can happen in case of an initial value problem. It may have a unique solution, it may have only no solution, or it may have more than one solution. For example, if we consider the initial value problem t dx dt minus 3x plus 3 equal to 0, the initial condition being x 0 equal to 0, then this particular initial value problem has no real solution. On the other hand, the problem t dx dt minus 3x plus 3 equal to 0 with the initial condition x 1 equal to 1 has one and only one real solution, and that is x t is equal to 0. And the same differential equation with a different initial condition will have more than one solution. In fact, it has infinite many solutions as given in C. When you look into a differential equation, the very first thing that comes into your mind is about its solution. How many solutions will it have? Whether the solution will exist or not. If the solution exists, whether it is unique or it has more than one solution. To justify these facts, we need to have a solid foundation of the theory of differential equation. The need for theory. It is observed that differential equations are usually originated as an effort of creating a mathematical model for the motion of physical system such as simple pendulum or simple spring mass problem. While modeling of the physical problem, we may use different physical approximations, and in the result we may lead to different differential equations. Please recall the differential equation for the simple pendulum starting from an initial angle y 0, which is a nonlinear differential equation as follows: d2y dt square plus g by L sin y equal to 0, given by equation number 10. Now, we want to use this equation 10 to find the motion of the pendulum satisfying the initial conditions y 0 equal to y 0, y dash 0 equal to 0. We will be surprised to know that there is no method available to solve this differential equation 10 in terms of any elementary function. But in the real world, a simple pendulum actually moves. This means our mathematical model is useless and have certain problems with a set of assumptions, and hence we need to construct a new model for the same, so that the new model may have some solutions. Also, we have seen differential equations which may not have any solution, but such solution may not be so important. Many physical systems are having real solutions, whether a suitable mathematical model is available or not. Therefore, to construct a useful mathematical model, we need to know that whether it has a solution or not. Thus, the existence problem, that is identifying the class of differential equation which admits solution, is indeed a very important problem of mathematical theory. Having conditions about the existence of solution is not the only requirement that is desirable for a use model. Since the problem relating to differential equation are originated from physical systems and expected to have unique solution for the given set of conditions. So, what we are trying to say is that if you have a differential equation of the form dy dx equal to f x y, the first thing you need to know that whether the solution of this differential equation exists or not. If it exists, then whether it will have a unique solution or whether it will have an infinite number of solutions, that is the thing which you need to check. Having conditions about the existence of solution is not the only requirement that is desirable for a useful model. Since the problem relating to differential equation are originated from physical systems and expected to have unique solution for a given set of conditions. There are many differential equations which do not have unique solution. Thus, we refer this problem, that is finding the conditions such that a differential equation should have exactly one solution for a set of initial conditions, as a uniqueness problem. Another important property regarding the satisfactory model is that if the initial conditions are slightly changed, then we expect the outcome are also slightly changed, and it is desirable that our mathematical model should also have this important property, that is, the solutions of differential equations depends continuously on the initial conditions. We refer this property as continuity of solution on initial conditions. So, given a differential equation, you first check whether the differential equation exists or not. Once you find the existence property is satisfied, you see whether the solution which you get is a unique one or it has infinite number of solutions. Once you do that, you check whether the solution, how much it varies with respect to the initial conditions. So, the properties which you have to look is the uniqueness problem and the continuity of solution on initial conditions. We consider the differential equation dx dt equal to x given by equation 11 with the initial condition x 0 is equal to 0. The solution of this given initial value problem is a trivial one, which is x t equal to 0. Now, if we slightly perturbed the initial condition 12 and take x 0 equal to some epsilon, where epsilon is a positive quantity, the solution of this perturbed system is now x t equal to epsilon e to the power t. Please note, the trivial solution is a bounded solution, but the solution of the same differential equation with slightly perturbed initial condition will be unbounded as t tends to plus infinity. Hence, we observe that a slight change in the initial condition changes the nature of the solution. So, once again, if you look into this solution, that is x t equal to 0, we see that this is a bounded one, whereas if x t equal to t e to the power t times epsilon, as t tends to plus infinity, this whole solution x t tends to infinity, and hence it is an unbounded one. And therefore, a slight change in the initial condition provides a massive change in the final output. Thus, a mathematical model of a physical system should have the following properties. Number 1, a solution should exist satisfying the initial conditions. Number 2, there exists a unique solution corresponding to each set of initial conditions. And number 3, solutions of differential equations depends continuously on the initial conditions. The above set conditions are known as well-posedness conditions for a mathematical model, and a mathematical problem having these properties is called a well-posed problem. Finding a well-posed mathematical model is a rare phenomena, and even for well posed problem, finding the solution in its explicit form is really very difficult. There are several equations whose solutions are not explicitly known, but have importance in many areas of science and technology. Please look into this equation x double dash plus pt equal to 0, which is quite innocent looking, but it cannot be solved for a general choice of pt, and yet it has many useful applications. So, for these kind of problems, we study the nature of solution through analytical considerations. The properties of solutions like existence, uniqueness, continuation of solutions, dependence of initial data, boundedness, stability, periodicity, asymptotic behavior, etc., provide the nature and behavior of solutions of these problems. Summing up this chapter, which consists of a single module, I have given you an overview of differential equations. Why you are learning this differential equation, whether the solution of the differential equation exists or not, if it exists, whether it is unique or it has an infinite number of solutions. These are the few questions which I have posed in this chapter. In our next chapter, we will look into the first order differential equations. Thank you.